I want to welcome you all and thanks for tuning into this session. Hope you're having a great day. I'm Anuj Devangan, a Principal Solutions Architect with AWS. I'm joined by Jonathan Lee from Dropbox, who will be describing Dropbox's metadata store on AWS. So let's start with an anecdote. So it's a given that as the data in your database grows, so do the costs for operating the data store. We have observed with several large customers that powered by the growth in the application, often the data backing the application grows exponentially. This in turn leads to overall infrastructure and operational costs exploding disproportionately over time. Looking deeper, there may be a cost optimization opportunity for the data that resides in your growing data store. Perhaps your older data that is not frequently accessed can be moved away from hot SSDs to a colder storage system. You may be surprised by how much of your data is cold. We have routinely seen examples where more than 80% of the data in data stores are accessed less than once a month. Dropbox was facing a similar challenge of disproportionately growing costs and operational overhead with their on-premises key value store. To solve this, Dropbox engineers were able to rapidly prototype and build a key value storage system on AWS. This storage system is powered by Amazon DynamoDB, which functions as a hot cache for storing and serving the data, while the infrequently accessed data is transitioned periodically and served out of Amazon S3 for cost savings. So if you're a storage architect, a database engineer, or a software developer, and you deal with petabyte scale data stores, a key takeaway from this session is how a key value storage system can be built using Amazon DynamoDB and S3, which cost optimizes on the cold data. We'll also dive deeper into DynamoDB's durability, availability, and scalability features, as well as share tips for scaling and cost optimizing DynamoDB and S3 in such a storage system. So let's look at the Dropbox story first. Dropbox operates an on-premises sharded database system for storing metadata for users and files, among other things. This in-house database system, called Edgestore, operates on top of MySQL and spans thousands of physical servers. In 2018, Dropbox was faced with a capacity crunch in this metadata store, as data in some of the partitions were growing very fast and the partitions were reaching capacity. Dropbox's database engineers considered a few options to solve this challenge. The easiest option was to stop supporting some of the business cases on Edgestore, especially where the data is cold and infrequently accessed. This would require the business owners, which were internal Dropbox teams, to migrate their data to a different system. However, this would also mean that the internal teams would now need to manage their own databases, which really is not an ideal outcome. A second choice would be to split the existing partitions on Edgestore and effectively double the size of Edgestore. However, this would also double the cost of running Edgestore, which is in the order of millions of dollars every year. So the choice was made to move to a different storage system for some of the metadata, especially the ones which were growing very fast. So starting May 2018, Dropbox started evaluating on-premises and AWS database solutions of Amazon Aurora and Amazon DynamoDB with S3. The key value nature of the workload made DynamoDB a natural fit for the use case. Dropbox's database team started building a prototype of a metadata store on AWS in October 2018, and within a short period of about 6 months, Dropbox were able to stand a database system for beta testing. During this phase, Dropbox rapidly iterated, built, and tested out new capabilities to meet the needs of their cold metadata. Following a migration of 300 terabytes of data from Edgestore to the new metadata store, the system went production in October 2019, serving live traffic for Dropbox's customers. Within a short period of a year, Dropbox's database team was able to build a distributed storage system that is highly available, durable, and scalable to petabytes of data, and importantly, saved them from doubling on-premises costs. So in this session, we'll first review the characteristics and architecture powering DynamoDB that makes it suitable for Dropbox's use case. A key takeaway would be the understanding of DynamoDB's fully managed availability and durability architecture, as well as the ability for DynamoDB tables to scale and adapt to traffic patterns. Jonathan Lee from Dropbox We'll then dive deep into the implementation of Dropbox's metadata store on AWS called Alki. Let's start by looking at how DynamoDB stores your data durably and is highly available for your operations, for which it is important to understand the underlying distributed architecture that powers the service. We'll start with a simple DynamoDB table which stores customer information. This table has a partition key of cust ID, which is also the primary key. Each item in the table has various other attributes like name, phone number, and address for the customers. Internally, DynamoDB stores tables across one or more partitions. For illustration purposes, I have shown 3 partitions here. The items in a table map to the partitions based on a hash function on the partition key, which is cust ID in this table. The hash value determines the mapping to the physical partitions underlying the DynamoDB table. Similarly, for a DynamoDB table with a partition key and a sort key, the data is still distributed across the underlying partitions based on the partition key value. The table here represents a customer orders table, and cust ID is the partition key and order ID is the sort key. Because the hash function only operates on the partition key of cust ID, data with the same partition key value maps to the same partition as seen in partitions 1 and 2. Let's see what a table partition looks like infrastructurally. We start with our example table with 3 underlying partitions. Each partition is represented by a set of 3 storage nodes. These storage nodes elect a storage node leader. Importantly, the writes to a partition are always sent to the leader, and from the leader, the data is eventually replicated to all the 3 storage nodes underlying the partition. So what does a write look like in DynamoDB? When a client writes an item to a DynamoDB table, in this case, a new customer information to our customer table, the put item request hits a DynamoDB endpoint, from where it is routed to a request router, where the request router calculates a hash based on the partition key and looks up the partition metadata table. The partition metadata table provides information on what partition the item needs to be stored. The request router then sends the request to the storage node leader underlying the partition, where the item is then stored durably. However, as Amazon's CTO Werner Vogels puts it very succinctly, everything fails all the time. We cannot assume that storage nodes are all going to be alive and store the data durably in eternity. Failures do and will happen. So how does DynamoDB manage failures to continue providing high durability? If a storage node fails, a DynamoDB component called AutoAdmin recovers the storage node by provisioning a new storage node for this partition, and then adds the new storage node to the partition, which triggers a full replication of the partition data to the new storage node. AutoAdmin also updates the partition metadata table as needed. As you can imagine, DynamoDB works on a large fleet of request routers and storage nodes. Like with any well-architected application on AWS, DynamoDB maintains availability and resiliency by spreading the infrastructure across multiple availability zones in a region. So a request from a client can hit a request router in any availability zone. Additionally, the storage nodes underlying a partition are also spread across 3 availability zones. So let's switch gears a bit and talk about scale. We have reviewed that the distributed architecture of DynamoDB allows the data to be partitioned and stored across several storage nodes. Because of this partitioning mechanism, DynamoDB tables can keep growing to any limit in terms of both storage as well as compute capacity. Let's see how this horizontal scaling works. First up, as the read-write capacity needs of your table increase, you can scale the provisioned read and write capacity of a DynamoDB table either using DynamoDB's built-in auto-scaling feature, or you can do it manually as well. In this example, as the RCUs and WCUs on the table were increased from 1200 and 3600 to 2400 and 8000, behind the scenes, DynamoDB rebalances the existing partitions and creates an additional partition to accommodate for the increased reads and writes on the table. So as you keep scaling your tables up, DynamoDB automatically rebalances the underlying partitions and in turn spreads the data and adds compute capacity to your tables. This is the essence of horizontal scaling. DynamoDB also automatically rebalances partitions if your partitions reach the maximum partition storage limit, like partition 3 in this case. And finally, DynamoDB also rebalances the partitions if a partition is receiving disproportionate read or write requests, which we are going to review shortly. Which really takes me to the partition heat map. It is important to understand that DynamoDB scales the best if the reads and writes to a DynamoDB table are spread evenly across the key space, and thus the underlying partitions. The heat map here shows that the heat on each of the partitions, represented on the y-axis, over time, represented on the x-axis, is evenly distributed as represented by the uniform color across the spectrum. It is important to module your data, including selecting your partition and sort keys wisely, to serve your reads and writes to get an even distribution as shown here. An example of uneven distribution here shows that certain partitions, shown in red, are seeing a lot more heat than other partitions, which are in the blue spectrum. Now, DynamoDB helps with uneven distribution of traffic through a set of features under the umbrella term adaptive capacity. We'll review a couple of features within DynamoDB's adaptive capacity here. Firstly, we have throughput boosting to high traffic partitions. This feature works by automatically and instantaneously increasing throughput capacity for partitions that receive more traffic. Let's look at an example to understand this better. Here, your table is provisioned for 1200 WCUs and 3600 RCUs, and we expect each of the three underlying partitions to receive an equal amount of capacity to begin with. However, if your partition 2 is receiving disproportionate traffic, with capacity boosting, you'll be able to consume capacity in partition 2 instantaneously up to the partition maximum of 1000 WCUs and 3000 RCUs. This mechanism works as long as the overall consumed capacity at the table is not exceeded. And interestingly, if your read-write distribution shifts to a different partition over time, that same 1000 WCUs and 3000 RCUs are available instantaneously in the new partition too. In effect, partition counts do not matter. And even if your table has a large number of actual partitions, you do not need to worry about any capacity dilutions at the partition level, as each partition is capable of serving up to the partition maximum capacity. Another feature under DynamoDB's adaptive capacity umbrella is dynamic partitioning. This feature automatically rebalances partitions in response to high traffic. In this example, let's assume a hypothetical DynamoDB table with a partition key of group ID and a sort key containing a unique identifier shown as UUID here. DynamoDB maps items with group IDs of A and B to the same partition in this case, which is partition 1 here. Now, if there is disproportionate traffic for items with group ID of A, then DynamoDB can rebalance partition 1 so that items with group ID of A are in a separate partition. This rebalance enables two outcomes. Firstly, items with group ID of A get additional capacity by not needing to share the capacity with other partition keys. And secondly, we prevent what is commonly known as the noisy neighbor problem. The items with group ID of B are now separated out, so they no longer need to compete with other high traffic items. Now, if traffic in the new partition for items with group ID of A is still disproportionately high, DynamoDB will further rebalance the partition so that there are multiple partitions with the same partition key value of A. Rebalancing partitions in this way allows DynamoDB tables to adapt and serve disproportionate traffic to certain partition keys. In summary, we reviewed quite a bit of content over the first part of this session. To recap, we reviewed that DynamoDB provides a fully managed key value and document database, allowing you to rapidly prototype and deploy your database to production without worrying about how the underlying partitions would be structured and scaled. All DynamoDB tables are highly available and durable out of the box, without the need for any configuration or added administration. The distributed architecture of DynamoDB allows scaling tables horizontally to any element, And finally, DynamoDB adapts to your traffic patterns through features like burst and adaptive capacity. With that, let me hand it over to John to explain how these DynamoDB features help Dropbox with their cold metadata store on AWS. Thank you very much for listening.
Thank you, Anuj. My name is John Lee. I'm a software engineer at Dropbox and one of the tech leads on our storage platform team. Now, before I dive into Alki's architecture and share some of the lessons we learned while building it, I want to give some more background about metadata storage at Dropbox to help you understand why we ended up building Alki. Now, at Dropbox, we store most of our product metadata in a petabyte scale distributed database called Edgestore that we built in-house many years ago. It works pretty well, and you can read more about it on our tech blog linked on this slide. But as Anuj mentioned, its inability to incrementally expand its capacity, coupled with some fixed architectural limitations around capacity, meant that we found ourselves in a bit of a capacity crunch in 2018. One of our largest product tables in Edgestore, which stores audit logs, had been rapidly growing, and we projected that this growth would cause Edgestore to hit some logical limitations in less than 2 years, causing the whole system to fall over. We needed to stop this growth or move that data somewhere else. Luckily for us, the product team that owned this table was pretty eager to move off of Edgestore because they'd been having a lot of load-related issues with Edgestore, which is built on top of MySQL. Their use case, which is a read almost never but write very often and retain indefinitely log of events, was a pretty bad fit for a database built on top of expensive SSDs and optimized primarily for low latency reads and high throughput reads. So we set out to try to design a second, more targeted, dedicated store for holding audit logs. Some basic requirements for the project to succeed from an infrastructure perspective. We knew that this table was already about 1/4 of a petabyte of data, which meant that whatever we built would need to be petabyte scale from day one and be easy to incrementally expand its capacity. And of course, because this data is being used to serve our API and admin dashboards to our external customers, we needed it to be highly available. And because it is user data, it also needs to be highly durable. Even though most of the data is never read, if it is, it had better be there. And most importantly, we needed it to be low engineering cost, to rapidly prototype, build, and roll out to production. Otherwise, we would run out of space before we could actually migrate audit logs off. Now, the audit log use case itself is meant for providing monitoring and visibility over their teams for our external business account admins. And one way that they can search for events is through sort of an admin dashboard where they can filter by certain queries. And this filter is then parsed through a secondary indexing system, which eventually results in sort of a number of point reads over data in some persistent store. So that meant that whatever system we built would need to be able to support point reads by some unique event identifier. And another way that admins can use audit logs is to subscribe to an event stream for their team using our Dropbox Get Events API. You can think of this as sort of an RSS feed style read. But also what this meant was that the vast majority of events, while being cold and are never read, newly ingested events are quite hot and in fact are read almost immediately after they're ingested. Now, there are also multiple streams that the admins can subscribe to for various ways to slice and dice the data, so we did need to be able to support queries over multiple indexes. And we also knew that because some teams were very large and some teams are very small, some teams would have very high volume events, while others would be very small. And this meant that the largest teams could potentially be generating spikes of up to 5 to 10% of the total traffic at any point in time. And for powering other products built on top of audit logs internally, the product team needed the store to support async triggers for when new events get added to. Now, some considerations. Before we set out to build the new system, we did look at a few off-the-shelf solutions to see what might be able to handle the kind of throughput that audit logs required. Among some of the options that we considered, we looked at on-premise running Cassandra or HBase. These are systems that we already use internally for our internal monitoring systems, or building something entirely new. But given the short amount of time that we had and the small team that we had, we didn't really have the confidence that we'd be able to gain operational expertise fast enough to operate these on the critical serving path for user data. Now, internally, we did have a lot of expertise operating MySQL at that level, So we looked at that as well as AWS managed Aurora and RDS, but those turned out not to be an option for us because through benchmarking, none of those systems provided the high single key throughput that we required for audit logs to support logging for large teams. DynamoDB did, however, fit the bill. Now, as Anuj mentioned earlier, DynamoDB has theoretically infinite write throughput, but more importantly, it supports very high single key throughput up to the partition maximum capacity for each item. And of course, DynamoDB is highly available, has a good track record for being durable and fault tolerant, which meant that we could trust it to serve this data. And we could build our async triggers using DynamoDB streams. But I think most importantly, as a managed service, with support from AWS solutions architects and their teams, we knew that we'd be able to leverage AWS to help us build and run this system with only a few engineers on our side. But the problem with DynamoDB is that it's optimized for hot data, much like Edgestore, while most of the audit logs that we store are very cold and almost never read. So as we set out to design Alki, we knew we needed to solve this problem with newly ingested data being very hot and then becoming very cold over time. So we started with a simple time-based bucketing approach. You bucket data by day as an approximation of sort of this hot and cold tiering of data, and when a new record comes in, we just insert it into the current active hot bucket. Now each day we'll create new buckets and seal the old ones, and you could take the older immutable buckets and then archive them somewhere like an S3. The problem is we still need to read this data, and for reads of some particular key prefix, the result may actually contained in many of these buckets. So for a read, we'd need to read from all runs and merge any of those results. If you squint a little bit, this very much resembles the leveling of a log-structured merge tree. Now this is just a popular data structure whose concepts are used in a lot of modern-day storage systems like Cassandra, HBase, and Bigtable. In a simple multi-layered implementation, when a write request comes in, it gets forwarded to some backend, and then it is written to an in-memory sorted table, referred to here as a mem table, commonly built on top of some sort of binary search tree. Now, since memory is limited and we can't continually write records to this mem table, we periodically flush it to disk as a sorted list of rows, referred to here as a run. And over time, you create more and more runs as you flush, and reads, because the data might be in either the mem table or on any of the on-disk runs, reads have to merge both results from the mem table and from all on-disk runs. But since everything is sorted, this can be done fairly efficiently, much like the merge part of a merge sort. And to bound the number of runs which need to be read by each read, typically we periodically compact the runs into larger and larger runs. And this process sort of occurs in several levels to reduce the number of times that we might need to rewrite a piece of data. As an observation, this type of structure sort of uses different storage tiers to optimize for different values. By using RAM for its mem table, it optimizes for the fast access of memory and being able to serve really fast reads and writes for recent data. And then by moving that data off to disk as it becomes colder, it optimizes for the much larger storage capacity of a hard drive. Now, some modern implementations will just omit the on-disk portion and just write the runs directly off to some distributed file system. In Alki, we took this a step further by just building the entire LSM tree structure on top of other distributed systems. So when a write request comes into Alki, we compute the keys for the data and then insert it directly into some daily tables per index that we keep in DynamoDB. Instead of periodically flushing to disk, we then just instead use AWS step functions and a batch processing system to help orchestrate a workflow to move data from our hot store to our cold store in S3. Now this periodic offload, again, serves to limit the amount of data that we store at any point in time in DynamoDB, and thus reduces our costs. Note that instead of storing a single S3 blob in S3 for each run, we actually store several blobs of some configurable size, about 1,000 records per blob for the audit log use case. And these blobs are keyed with a randomly generated ID, which helps us achieve higher S3 throughput in conjunction with S3 partitioning. So we keep a metadata table in DynamoDB called the blob index, which helps us track these blobs, and we can use it to query for a record in any run. It's just a sparse lookup table with the data run as the partition key, and then the key of the first record in each S3 blob as the sort key. And like a traditional LSM tree store, over time we'll accumulate more and more data runs in cold storage. When reading, we will again read from hot data and then merge the results from reads from the cold data. And of course, in order to bound the number of runs that we need to read from, we do also perform periodic compactions of the S3 data runs, similar to the traditional LSM tree structure. By using this LSM tree structure as the foundation of Alki, we're able to take advantage of DynamoDB's high throughput capabilities, combined with the advantage of using S3, which is very optimized for long-term storage and archiving data. And by using these fully distributed managed systems as the building blocks, we were also able to go from whiteboard to production ready to data migrated and served from Alki in just over a year, with about 2.5 engineers working full-time on the project at any point in time. And the migration itself was very simple. We created a new data run, and we uploaded data directly to S3 and updated the corresponding rows in the blob index as needed. And since both storage layers were horizontally scalable and easy to be provisioned, we were able to scale up our ingestion throughput by about 100x and do most of the ingestion of the 300 terabytes of data in over a couple of weeks' time. Along the way, we did learn some lessons and tricks that I want to share. One problem that we had with DynamoDB's dynamic data repartitioning is that it can take up to several minutes for it to split a hot partition. So we knew ahead of time that we were always going to have hot partitions in our daily tables due to sort of uneven ingestion of audit logs for teams of varying sizes. So our solution here was to set the provisioning at table creation to much higher than expected, and then lowering it immediately after creation. The idea here is that this will force DynamoDB to create more backend partitions right off the bat to serve the data for the table, and then that way we wouldn't have to take several minutes of unavailability at the start of each day. Now, we do also use reserved and provisioned capacity units on our table to help reduce our IOPS cost. And one issue we had with DynamoDB is that its CloudWatch-based autoscaler takes too long to adjust provisioned capacity units. So if we have a read or write traffic spike, which then suddenly becomes the new steady state, this could cause many minutes of availability outages. And so we mitigated this by implementing a custom autoscaler daemon that monitors capacity usage in near real time using describe table, and then directly updates the provisioning using the update table API. Another issue we designed around was with limitations of DynamoDB's two built-in secondary index options. So our feed API needs to paginate over data in a secondary index over some sort of Alki insertion time. And we couldn't use the local secondary indexes because of limited throughput due to shared provisioning. But we also couldn't use the global secondary indexes because those are eventually consistent, which meant that we would not be able to guarantee that all records with some sort of range of insertion timestamps would be readable by the time that we read it. Now, as a solution, we ended up just creating entirely separate tables per index and inserting items into those tables for each row using some sort of batch insert API or the transact write items API. For S3, for compliance reasons, sometimes we do need to purge large groups of objects in Alki within some sort of fixed number of days. The idea here is if some external Dropbox customer requests their data be deleted, we need to do this for compliance purposes. And in order to prevent needing to delete large numbers of data in a short period of time, we just encrypt every object in a logical purge group with some encryption key. And then when the group of objects need to be purged, instead of having to issue individual deletes for each object, we can just delete the key, effectively shredding the data, and then turning the deletion of objects into a long-running async garbage collection job. Now, we did also optimize for our S3 API costs by storing a full copy of data for every index. So we normalize the indexes. And the idea here is that for a read range over the data in that index, all the data would be right there in the blob, and we wouldn't need to sort of read one blob from the index and then do 1,000 indirect blob lookups in the actual main index. Now, before I wrap up the talk, I do want to share a little bit about the current scale of Alki and our future plans. By effectively storing metadata in S3, we've achieved about a 5.5x cost saving over our main metadata store per gigabyte per year. And we have about 320 terabytes of growing, uncompressed, unindexed user data, and we continue to maintain the system with only a few engineers. We have daily about 5,000 WCUs, write capacity units for each index, and this produces about a daily table size of 60 gigabytes per index. And we are currently migrating some of our in-house jobs over to Amazon EMR and Hive. And we are also onboarding a second use case with another about 300 terabytes of cold data, with more use cases lined up afterwards. Going forward, we're continuing to work on reducing our read, write, and thus cost amplification. We are looking to support other hot and cold stores within Alki to optimize for different use cases. Since we built Alki, AWS, as an example, now has a managed Cassandra, which could be an interesting hot store implementation. And long-term, we're trying to position Alki as the de facto cold metadata storage layer within Dropbox and continue to onboard other large use cases and save money for the company. I want to briefly thank the many AWS teams for their support in building and maintaining Alki. Their design advice, debugging help, and openness for feedback has made the Alki project possible. Out of our partnership with AWS, DynamoDB has prioritized and implemented several features and improvements over the last years. They've removed a layer of provisioning checks at the partition level, allowing any partition to sustain up to the partition level maximum, assuming the table itself has enough capacity provisioned. They've also built dynamic repartitioning to isolate frequently accessed data to their own partitions, allowing for sustained high single key throughput. And they've also integrated global admission control transactions along with their global admission control support for their transactions feature, which helps reduce overthrottling. And there are many more features on the way. Thank you for listening to our talk, and please complete the session survey.